All right, welcome everybody to the topological complexity seminar of the Applied Algebraic Topology Research Network. And today our speaker is Shmuel Weinberger, who will talk to us on analog and universal complexity. Shmuel, take it away.
Okay. Thank you. Okay, let's see. No audio. Okay, share content, screen. Broadcast. Okay. Okay. All right. Yeah, so what I want to talk about today grew out of conversations that I had a while ago with Misha Farber, but that I've been working jointly on, mainly with Ben Knudsen at Northeastern. And here's a picture of Ben, and some of it towards the end will be joint with my colleague Nick at University of Chicago. Okay, so in order to spare you my terrible handwriting, to the extent that I can, I'm going to try to refer to papers. And our subject starts, I think, the topological complexity idea started with a paper of Steve Smale many years ago, 1987. And what he was he sort of observed that there are topological reasons why it's not so easy to actually, right? There's a simple topological reason, proof of the fundamental theorem of algebra. Okay, but on the other hand, if you want to, topology also, maybe a little paradoxically, indicates that the problem of finding a root of a polynomial is a little bit more difficult. Okay, and so this is the paper, and he was studying the following. You consider the general problem so that you have a polynomial of degree n with complex coefficients. Okay, and you think about the problem. So you have a n coefficient, so you have something defined on Cn, and then your goal is to output just output a root, right? I mean, you imagine you're going to put it into a computer and that the computer is going to do some kind of calculation. Okay, so there's a certain amount of I'm not going to go into great detail on the paper. Although, again, for the young people who don't remember when this paper came out and how beautiful it is, I highly recommend reading it. I mean, sort of the early papers, very frequently have more to recommend them than what memory says. So, so he talks about, maybe you're going to be outputting from your algorithm something that's close to the root, etc. But in any case, let's just imagine that you want to assign the roots, and you have even very powerful nodes that are computation nodes, but that there's you just can't go ahead and do it, right? The output of a computer is going to be, if it's a degree n polynomial, you can imagine it's going to output ultimately n roots, but they're going to be output, on n lines. So you just ask for the first line of output, what is the first root? And the way he measures the complexity is he imagines that there's some computer program, and that at each node it either does a computation, it might do a test, and that if something is greater than or equal to 0, you do one test, you do one kind of computation. On the other hand, if it's less than 0, you do a different calculation, right? So there are these forking steps in the course of a computer program, and the question is that as you vary the coefficients, how many different kinds of paths through this kind of tree? So we're not imagining that the program loops back to itself. If it does, you should really look at, so to speak, at the universal cover of the program, so that it's really a tree. And the question is, how many paths through the tree do you see during the course of solving this problem, which the fundamental theorem of algebra says can always be solved? And his observation is that the only place where you get discontinuities are, of course, from the forking, right? When you do a decision, and that if something's greater than 0, you do one thing, and if something's less than 0, you do something else. And what you're trying to do is you have this function that goes from Cn, Cn, which you think of as being the roots of the polynomial, but it's invariant, of course, under the symmetric group when you assign the polynomial whose roots are those u's, right? So you have u1 through un being root space, so to speak, right? Those are the n roots of a polynomial. Then you take z minus u1 times z minus u2 times z minus un. Okay, and that will be the unique polynomial. And of course, the computational problem, phrased this way, is just a matter of, you want to find a section, right? So you had u1 through un, and you're trying to go ahead and pick one of them to be the thing that your computer program does. And this can't be done in in any kind of continuous fashion. It's even obvious for the equation z squared minus u, as u goes around the unit circle, right? There are going to be 2 square roots, and they get interchanged as you go around the circle. So you're forced to have one discontinuity. So, Smale in this paper, he introduced this notion of complexity. He used results of Fuchs, of Dima Fuchs, about the cohomology of configuration spaces of non-colliding particles in the plane. So that meant that in solving this problem, instead of working on the whole target Cn, right, of all polynomials, he focused on the complement of a certain discriminant locus. Okay, so that in the complement of that discriminant locus, this function was actually a covering map. All right, or a fibration that tends to make the algebraic topology, the problems of finding sections more conventional algebraic topology, and then the problem about finding sections. This he reduced. He didn't fully analyze it. Much better work was done later by Vasiliev, but he got some estimates just by using cup length estimates. Okay, right, where the fundamental version of this cup length estimate, I don't know, at this seminar, I don't probably have to tell anyone about this, right? This is a generalization of the basic idea of Lusternik-Schnirelmann category, right? Where, if you'd be having, say a cohomology class that's going to be vanishing on, many particular open sets, then then some power of it will vanish on the union of those. Okay, so anyway, so that was Smale's original. I mean, this paper has had lots of implications for other communities. I mean, this model is, I think, a prototype of what's ultimately the Bloom-Kucher-Shube-Smale model in numerical computation. A fascinating project. But the next thing that's relevant for our story was this seminal paper of Michael Farber, where he began applying this to robotics. And this is what this seminar is, the topological complexity seminar is largely about, this model. And, while robots have to do, many, many things, right? One thing, right? I mean, the main way in which a robot is different than a computer is that a robot functions in the real world. It's not just a Turing machine. It doesn't just take in data and spit out data. It has to function in the real world. And one of the things that the robot will do is it will move from place to place. And that was what Misha focused on. And so that was what was, so to speak, the main problem. You might be given a point A, the robot might start at a point A, and then it has to get to the point B. And that was the problem that, whose complexity Misha focused on, right? So that, you have, the robot is, say, in a room, okay, or it's in the solar system or wherever it is. and it will be in some initial position, and it will then be instructed go somewhere else. And the robot has to then go ahead and describe a path from the point A to the point B. So if you have some initial space X, okay, then the input is a point in X cross X, which you interpret as being an initial point and an endpoint. The output that the robot is supposed to produce is a path in the space X, right? So this is not based paths. So the space itself is homotopy equivalent to X, okay? And then similar to Smale, he was asking, how many different planners do you have to do, right? I mean, in the course, you imagine the robot will be having some kind of program, so there'll be some amount of forking. In some places or other, it's going to be making decisions that will force a discontinuity. And, that was the idea. And that, you imagine that, among all the other problems that the robot designers going to do, they're going to have to need some routines in the chips where they design the robots, and according to the difficulty of the job that the robot is going to have to do in terms of its workspace, that will be causing complications into the program. Okay, in a little bit of a later paper, Misha considered other implications of this idea about about what does this mean besides for the complexity of the of the planning process. Okay, so he has a theorem in this paper. Okay. Called the equality theorem, which says that the four notions of complexity introduced above coincide. Okay, so I'm not going to tell you what all four are. I've already told you about one of them. Okay, and I recommend this paper because it's sort of, besides mathematical results, it's also an issue of, the modeling that was the initial goal, of this, of this project. So one of them is sort of the amount of instability that a robot has, okay, which is this, that not only do you need to have a lot of places, not only do you need to have a lot of different subroutines that the robot is going to do, that in this point in X cross X, you use one method for finding the root, and for another place you find another method. If all those places were disjoint, then you would just call the union of those one method, right? That would still be a continuous function. Okay, so from the point of view of this modeling, it wouldn't make a difference. So the real point that Misha emphasized was that the topological complexity, measures, how many of these have to intersect each other. Okay, so in other words, at a point like this that I've drawn, that green point, there's sort of a threefold. Not only is it that you need to have, a motion planner A here and a planner B there and a planner C there, there's also this point, that green point where there's a threefold instability. Right, so that if you wanted to understand, if you're at that point or you're near that point and you have just small measurement changes and you're trying to predict the future actions of your robot, which presumably manufacturers of robots would be interested in doing, right? The topological complexity also gives you some information about the instability of the future trajectories of robots. Okay. But that's not what I'm talking about today. I mean, I think that that's sort of an interesting thing. Actually, what I'm interested in is sort of the randomness. Okay, so Misha imagined that you might go ahead and, I think that we're all familiar with the idea that, it's not a theorem, but it's something that's certainly true in practice, that that randomized algorithms are many times more efficient than than deterministic algorithms. Okay, I mean it's still an unsolved problem, the extent to which randomization can be removed from ordinary computer programs. So the question is, what happens if you were going to give your robot some amount of randomization? Okay, so Misha imagined that, well, here I have the A, B, and C, so there's sort of three pieces of randomization, right? Right, and that you imagine that, at the points within the A line, within the A zone, you definitely do A. But as you get near the A-B barrier, you have more of an odd as you get closer and closer to the barrier, of doing a B instead of an A. That's, a different way of thinking about this instability. You could also think about it probabilistically, so that when you're exactly on the border, it would be like a 50-50 chance. And then when you go into the B zone, then you begin 60% B till it's 100% B. And then, of course, at the green point, you would need to have a probability measure that would have support on 3 points, right? So that it wouldn't be 50-50, it would be 33, 33, 34, or something like that. Okay. And so then Misha introduced this other notion, okay, about the probabilistic this kind of probabilistic planners, which are that, and you have to be a drop careful about what you then mean by the continuity, but the thing you guess is the thing that works, so I'm not going to discuss it, right? I mean, once you begin being probabilistic, then of course, the prediction that you make isn't going to be a deterministic prediction, right? I mean, it's sort of like weather. Anyway, and then the ultimate theorem, the beautiful theorem with Misha's definition is that all of these different kinds of notions which measure different kinds of instabilities or difficulties or complexity, that all these notions are in fact the same as each other. Okay. Okay. And let me also mention one more beautiful paper, which I want to call a contrast, which I will soon be contrasting to, which is this paper of Misha, Tabachnikov, and Uzvinsky, which I think is, it's really a milestone in the subject, where they calculate what happens for RPN. Okay, for spheres, right, this was in Misha's very first paper, and that there's a difference between odd dimensional spheres and even dimensional spheres about what, but for RPN, it turns out that it becomes, it's related to this very, to the problem. It was a classical problem in homotopy theory of immersion theory, and the number of and the top, right. So I hope you could see it here in the yellow, right. That the topological complexity of RPN is that, except for the 3 cases where RPN is actually parallelizable, so it immerses in codimension 1, it boils down to being the smallest integer k such that the projective space admits an immersion into RK minus 1. So this is a very delicate thing. And here's a little table from that paper. Okay, and that paper and that result is of course correct. Okay, but what I'd like to ask you is this really the complexity? If I were on RPN and I give myself access to randomness, okay, is that really the right complexity, right? So I'm going to ask you to make a mental picture now. So this is a mental picture of RP23. Okay, so the topological complexity according to this table is 39, right? So we need to have 39 motion planners on RP23 cross RP23 in order to navigate. But let's just think about it. So I have 2 points. So this is my starting point. Okay, so that's where I start. Okay, and okay, here's where I end. And I want to go ahead and motion plan on this. So let me, I mean, I think we've all lived on RPN at some point in our lives. So what happens when you're in RPN, you start off where you are, okay? And, so living on RPN is a lot like living on SN, but then you identify opposite points. So, so all the geometry really you could imagine is you're at the North Pole because because life is homogeneous. Okay, you're on the North Pole. Then you have in the whole northern hemisphere, there's a unique geodesic that connects you to the point, right? So if the start point and end point, are less than, right, I guess, is that pi over 2? If they're less than pi over 2 apart, right, there's a unique geodesic that connects you to that. And obviously that's how you're going to motion plan. Okay, the problem happens when you're exactly pi over 2 apart, right? Such that the other point would be something whose twofold cover lies on the equator. And the trouble is that there are 2 points on the equator, right, that that cover this point downstairs. So when the endpoint, so the real problem is really, right, when the endpoint lies on the equator, okay? And in that case, there isn't a unique shortest geodesic, but there are, of course, 2 unique geodesics. There are 2 geodesics. I can't say 2 unique ones, right? There are 2 geodesics that, right? I mean, and, and they sort of are, I just go in opposite unit vectors, when I'm going to be exponentiating down to them. Okay, so now, here's, certainly this is what I should do if I wanted to do something non-deterministic, right? I start at where I am, I, click one of those spinners that a little kid has, that the little kid has, I forget which games they have it because I'm so old, but I'll remember soon. Okay, and then I pick the, with probability 1, it's going to be near one of those 2 vectors. It's going to be nearer to one of those 2, and that's the one that I choose. Okay, now you're going to say that's discontinuous. So what happens is that as I approach pi over 2, I begin giving myself some slight probability of doing the longer of the 2 vectors. Okay, there's a unique one to choose, and then I might, with some probability for a little neighborhood of the equator as the target. So, one would really feel to want to say that no matter what, the random topological complexity of RPN is 2. Okay, because that's clearly right. Okay, now, are there any questions about this? I mean, I've settled a little bit of tension here because Misha's of course right, and I'm of course right. So one, there's an obvious question that's on the table. But does anyone have any other questions before I proceed? Okay, so the reason that Misha is right is built into his model. Okay, so what was he doing? He was, again, thinking that we had this, he was thinking along the lines of a computer chip and what the computer was going to actually do. And then when so what does it do? His understanding of randomness is there's a node which flips a coin. And if the coin is head, it says go to line 100. And if the coin is tails, it says go to line 222. Okay, right? That there has to be some specific protocol that it follows and that you have to be able to verbalize it. Okay, so that is what one would call a digital source of randomness, right? Your flip, right? I mean, that the whole program is in there. What I told you to do is, you go ahead and, it's analog, right? I mean, you're flicking the spinner goes around and it more or less points to the direction of which of the 2 vectors you should choose. Okay, so that's an analog process. Okay, you're not verbalizing, so to speak. Nowhere or other do I have to identify this is the first choice and this is the second choice about where I'm going. Okay, which if you think about it, that's exactly the source of the difficulty for Smale. If I would have to go ahead and describe a polynomial, okay, right? And I was, I never heard of coefficients. So the only way that I describe polynomials is by giving a bunch of roots. And then I'd be forced to verbalize my polynomial by saying U1, U2, U3. And then, of course, there would be no trouble about finding roots. The real problem is the fact that they come up in some unknown order. Okay? So, so sort of built into this subject, right? So if you would be trying to go ahead and solve a problem, but you allow yourself to be probabilistic without, you assign something a measure on a set without going ahead and giving names to the elements of the set, right? So you're going into a space of probability measures on a fiber, okay? So, right, so that's what you want to think about. So here I have x going down to y, okay? And I just have a function, pi, and instead of having a section to x, okay, that's a kind of thing that's difficult. Suppose that my section was going to be going into the measures on pi inverse of the point little y. Okay, I guess M would be a good name for that. For that thing, right? So obviously, if I allow all measures, right, then the particular, all the fibers would become contractible, spaces of measures. Well, if it's not the empty set, okay, right? I mean, so, but right, so I want to do, and so these should be probability measures, okay? Then all of a sudden, this becomes a doable problem, okay? And I'm not going to worry about the semi-continuity properties, et cetera, for you to really build a selection function. Okay, I mean, there are sort of point set functional analytic property problems, which, but in this algebraic topology world that this seminar usually lives in, this would be a fibration, and so would be the space of measures. And then when you're having contractible fibers, we'd have no trouble building it. Okay, so that would be if we were going to be completely probabilistic. Okay. But of course, to capture the spirit of what Misha was introducing was he was asking about how much indeterminacy is there, right? So you want to be looking at measures whose supports are on k points. Okay. And that this is a notion that seemed interesting to us because it captures some aspect of the difference between analog computation versus digital computation. The fact that you don't have to, so to speak, give a name to what the next step in your procedure is going to be. Okay, and it seems relevant to robotics, and let's see. Okay, so this is a notion that Ben Knudsen and I wrote a paper about called analog category and complexity. A couple of days before we put our paper on the archive, Sasha and Jauhari, who I never met, who I assume is a student of Sasha's, put another paper on with a very similar notion. I'm not going to say much about what their notion was. They had a different motivation, and that's in fact what the cover of this thing. That's Terminator 2 up here. Okay, this is when he gets riddled with bullets so that you could really see the liquid metal. And they were interested in what happens if instead of just, if your robot was Terminator 2, and you want to do motion planning for it because it gets to break itself up into pieces and do a different motion plan for each of those pieces. But again, you don't have to, the pieces being, I'm not sure where, who confided the details of the technology, to Sasha. But anyway, the assumption was that you wouldn't really have to identify everything very carefully. So it's a very similar notion. But I'm going to mainly focus on this idea, this analog complexity idea. Okay. Okay. So Sasha wrote a paper recently okay, so let me just see. So here I have this note to myself to sketch. Oh, okay, that for any torsion-free group, we have that the analog complexity of BG is the same as the cohomological dimension of BG. So, okay, so I will follow my notes, so to speak. Okay, and so by the way, the analog complexity here, I'm not talking about the analog topological complexity. So I'm talking, this is sort of the analog complexity in the sense of like Lusternik-Schnirelmann category. Okay, so over BG, right, you have the universal cover, which is EG. Okay, and right, so that's sort of the contractible thing. So when you're doing Lusternik-Schnirelmann category, you're asking about the Schwartz genus. When your base is aspherical, you're asking about the Schwartz genus of the universal cover. Okay, and now over a fiber of this, right, you of course have G, and inside of this you have inside the measures of size K and G. Okay, right, I mean that's what one's asking concretely about. Okay, well, if I have a discrete set, okay, the measures of size 1 are just a discrete set itself, right? A measure of size 2 is exactly, I'm forming, all of the possible 1 simplices. It's the complete, the English word is, it's the complete graph on that discrete set, right? Right, that associated, a measure whose support is on these 2 points is something like this line, right, that's connecting those two, okay, that there's going to be a coefficient between 0 and 1, that connects those 2 things, okay, and that when it's 1, then I'm at this point. It doesn't really matter, I mean, it carries the fact that, it has the right topology and so on and so forth, right? So, measure sub 2 would be the 1 scale, would be the complete graph. Measure sub 2 would be, all three tuples of group elements will be forming, triangles, and so on and so forth. Okay. Okay. Now, the group action, if G is a group that doesn't have torsion, and I consider any of these M sub Ks, all right, let's just think about, if G acts on it. So, how do you get something to have a fixed point, right? If you have a little element, little g, that's going to be a fixed point, I have to have h to hg to h squared g, right? I have to have an invariant simplex somewhere. Okay, so when I have torsion, I begin getting invariant simplices. But if I don't have torsion, it's a free action. Okay, so now you can see what's going on. So when I go to MK mod G, right, which is what I'm supposed to be doing. Oh, I have to get the screen back. Okay, right. This thing here is going to be a k-dimensional complex, and it certainly has a map to BG. And you're asking about a section. But of course, the cohomological dimension is the dimension of the smallest complex. It's the smallest dimensional complex that has BG as, as a retract. Okay, so this analog Eilenberg-Ganea theorem, is pretty straightforward. Just thinking about what the definitions are and, and just working it through. Okay. Okay, so similarly, so this paper of Sasha's is a very beautiful paper, and with his definition, he proves that for Z mod P, again, the analog complexity or the distributive complexity of Z mod P is exactly P. Okay, that, and of course, if I have P things, there's an obvious non-deterministic measure to use, namely just weight each guy with 1 over P, right? I mean, that's sort of, that's sort of the thing to guess. all right? But if you think about it, right, I mean, the proof is, again, pretty straightforward. You want to look at measures with support of size p minus 1, right? That would be the most extreme case. That would be lower, right? I mean, of z mod p, okay? This is going to be a sphere SP minus 1. Okay, what is it, right? I mean, it's everything in a P simplex, except for the top part of the simplex, right? It's all the faces of a P simplex, right? So the boundary of it, so that's the boundary of the simplex. So that's a sphere of dimension P minus 1. Okay, and this, as we mentioned before, it still has the free action. Oh, okay. Every time I touch this, there's a chance that I interfere, right? And you could identify which length space it is. I won't bother, but but it's a length space of dimension P minus 1 with fundamental group ZP. Okay, so now you're asking, does there exist a section? And firstly, and the answer is of course not, right? Because, for example, the cohomology of BZP is non-zero above dimension P. Okay, right? So I mean, it just doesn't satisfy the cohomological conditions. It's a Borsak-Ulam theorem, if you like. Okay. Okay. Oh, this one, so okay. Yeah. I'm following my notes. So about what I should talk about next. Okay. So another case that you might consider along the same lines. Okay. This one took a little bit longer. Is we're going to imagine we have n, that we're living in Hilbert space, H, some big infinite dimensional Hilbert space. And then I'm going to take n unordered points, that configuration space. So this thing here is, in fact, the classifying space of the symmetric group on n letters. Okay. And again, you could ask, what's the analog complexity of this, right? Which this feels like, oh, you just choose n distinct points. Okay, under a very, right, you're just choosing n distinct points. You have to choose them somewhere, so you put them in the biggest place that a normal human being would put them. Okay, and you want to figure out, is there any principled way of making progress? If you like, right, these are n voters, each of which has their own opinion about something, and maybe there's some adjudication that needs to be done, and you don't have any structure on the space of choices, so you think, okay, I'm going to have to randomize. So the most obvious way of doing a random election might be, okay, there are various things you could, when your space of choices is non-contractible, elections are very hard. So one way to make it contractible might be to use money, and and then you get the cone on the space of choices, and you use an extra direction in order to feedback. Another method you could do is just at random pick one person in the population and just do whatever that person wants, right? And that's sort of like an election, because 51% of the people agree they have a 51% chance of choosing that person's candidate winning. So I mean, I'm not literally proposing this, but but if we're telling stories, it seems like a story to tell. So now you can imagine that you're making some progress, in elections would just be replacing endpoints by a measure that is fewer than endpoints. And of course, it's intuitively obvious that you shouldn't be able to do this. And I just want to argue that, of course, you can't. Okay, but it needs an argument. So the case when n is prime, we already did, right? Because BZP, is a cover of B sigma n, and we couldn't even do it maintaining that amount of symmetry, right? Saying that you're symmetric under the whole symmetry group is a strong form of democracy, right? It would still be arguably democratic if you had a transitive group. of automorphisms of your electorate. Okay. And now the point, so the question is composite, and this unfortunately held me up for about a half hour until I realized that if n is composite, it's divisible by a prime. Okay, so then you just imagine Z mod P acting on that, on K copies of Z mod P, and then you just do the same argument. Okay, for a little while I was thinking, oh, is there going to be, is there a connection to the Riemann hypothesis and the gaps between primes, et cetera? But there isn't. So there's nothing that nothing surprising yet. But now the question, but you could begin asking this question now for other groups. And for P groups, so right, the obvious estimate is that, right, the analog complexity of BG is obviously at most the order of G, right? And that's explicitly just by, weighting each point the same way. Okay, and the comment that I want to make is that algebraic topologists have known for a long time that this is an interesting question, because what are you actually studying? I mean, we're using this terminology of sections over BG, but that's what we call the homotopy fixed set. If you have G acting on a space Z, okay, and then you look at Z cross over G with EG, and then this maps down to BG. So let me just write this out, Z cross EG over G. Right, so you've freed it up, and then you ask about the sections. Okay, right? This is what people call the homotopy fixed set. This is by definition ZHG. It's the homotopy fixed set of this. Okay, and of course, the genuine fixed set of G acting on this set is a subset of the homotopy fixed set, which you interpret as being the constant functions. Okay, right? Those are the obvious sections. Okay, and all that I was, doing was, just checking something or other. And the basic point was that when we look at the action of G on MK of G, okay, and if there's no fixed points, then we're hoping there are no homotopy fixed set points. And that was a great conjecture of Dennis Sullivan's, that if you have a finite complex, okay, or maybe finite dimensional even, you could go ahead and, do such principles. So this is from Sullivan's, this is from Renitzky's teching of Sullivan's 1976 notes. So for many years, this was an informally circulated mimeographed document. But Andrew teched it up and published it, and it's still available on his webpage. So anyway, so this was Sullivan's conjecture, which was, by the way, a beautiful conjecture. It's worth looking in the original source, looking at the pages before it, because what his goal was to give an étale homotopy theoretic description of real algebraic geometry. So he was thinking about it as being complex algebraic geometry together with that involution. Okay, I mean, so that was the motivation for all of this. But in any case, the theorem is that. So this was sort of the first major step towards the proof of the Sullivan conjecture, where the group action was the trivial action. Okay. And then there were a few solutions to this conjecture by Gunnar Carlson and by Haynes Miller and by Jean Lann. But in any case, the Sullivan conjecture is in fact a theorem. Okay, it's a little bit more complicated to phrase when the fixed point set is not simply connected, because all of this stuff really takes place in the world of completions. Okay, but let's ignore the subtleties. But the basic point is that the upshot of all of this, deep homotopy theory is that for P groups, also the trivial estimate is the best estimate. Okay, right? I mean that, you just go ahead and look at the measures. It's a nice set of, it's a nice, beautiful finite complex. You see whether it has a fixed point. If it does, then obviously that's what you use. And if it doesn't, then thanks to the theorem, there is no section. Okay, the homotopy fixed set is empty. So that proves, the obvious thing for P groups. But it turns out that, and I think that this is well known to a certain set of people, but it's maybe not well known to everyone, which is that if you have a composite order, though, then homotopy fixed sets and fixed sets really don't resemble each other very well at all. Okay, and at least for nilpotent groups, in fact, I mean, in general, one can prove, although I'm not going to give the proof, okay, that the analog complexity of BG when G is finite, and this is something that will appear in a paper of Ben and mine, is that this thing here is less than 3 times the order of the largest CELO subgroup. Okay, so okay, I'll explain it in so in other words, if your group is Z mod PQ, okay, instead of it looking like PQ, it looks roughly speaking like 3 times the larger of P or Q. Okay, so now this is sort of a little bit weird, by the way, when you think about it, right? I mean, I don't want to revel in how weird it is for more than, except among us geeks, right? But if you just think about it, right, you're having PQ points and you're being democratic, but there is somehow some principled way of saying that I'm going to assign a measure on a proper subset, that I'm just going to throw away some voters. And I'm not going to weight everybody else equally or anything like that. I can't do that. And then, as I move through my universal space, this is actually something that's doable. It's hard to imagine that any of this really, makes sense in the application to democracy. But that's what this theorem is asserting. This calculation is asserting is that there's somehow a way of going from, when you have your group that's not a P group, okay, with some small exceptions, right? Like twice a prime turns out to work out like a prime. But, by the time you get, to reasonably complicated groups, not very, like Z mod 15 or something. No, 15, 3 times 5 doesn't beat it. Z35, okay? You begin seeing that you could do a little bit better, okay? And, oh, I realize that, okay. All right. Anyway, so the key to this is another old paper that appeared this is in the Bulletin of the American Math Society in 1958. So let me explain this old paper of Connor. Oh, that's my 10-minute warning, which says that I should be wrapping up. Okay, which I guess I will soon be doing. Okay. So let me explain this paper of Connor and Floyd. And they were interested in, you have Rn. Okay, this was 1958. Okay, so you have to know we didn't know very much about anything back then. Okay, but what we did know was that P.A. Smith showed that if G is a P group and you act on Rn, then there's some fixed point. Okay, Smith was a little bit unhappy because he was, he would have liked, he showed that the fixed set was mod PA cyclic, and he thought that was really a bad result because he should have shown that it's contractible. Okay, right? I mean, he was dissatisfied, with what he had done, not realizing at the time that, of course, that was the best that you could do. Okay, this paper of Connor and Floyd showed they were dissatisfied because what they did was they were studying this for Z mod PQ. Instead of acting on Rn, they only produced it on a contractible manifold. not much later than that, Stallings would show that any contractible manifold crossed with R is a Euclidean space. So the actions that they produced on contractible manifolds automatically produced actions on Euclidean space. Okay, so what I want to just do is explain, and I'm not going to explain the manifold theory behind it. It's not very difficult. My time is pretty limited, but here's sort of how it goes. So you think about S1, and it has a Z mod P action, right? Just rotate by 2 pi over P. Okay, and now I could take the map, Z goes to Z to the R, okay, when R is congruent to 1 mod P, and that will be equivariant. Okay, and I could do a similar thing, Z goes to Z to the S, for the action of Z mod Q. Okay, whenever S is congruent to 1 mod Q. Okay, so now think about S1 join with S1 equivariantly. So this has an action of Z mod PQ. Okay, and this, of course, has a map to itself. Okay, so I'm going to draw this as it, okay, I'm sorry. My 3-sphere looks like a 2-sphere, alas. Okay, so this is a map of degree, R minus 1 times S minus 1 plus 1. Okay, I mean, whatever. I mean, you can figure out what the degree is. Okay, and now from such a map, what I could do is I could pinch off along a free orbit. Okay, and on this, take any map from the 3-sphere to the 3-sphere. Okay, and then just move it along using the group action. Okay, so they observed that combining all of these, you can find G mapping S3 to S3 that's equivariant, and that's equivariant and degree equals 0. Okay? Okay, cool. I mean, it's sort of very anti-Borsuk-Ulam, right? Borsuk-Ulam says for involutions, a self-map, equivariant self-map has to have a degree. Right here is saying for non-prime power phenomenon, there you can get the degree to be anything you want. Okay, more or less. Okay? I'm paraphrasing. So now what they do is they just take the mapping cylinder, S3 going by G to S3, going by G to S3, etc. Okay, take an infinite telescope of these mapping cylinders, right? You just do. And the point is that this space here, call it X, is contractible, right? Because these maps are null homotopic. Okay, so, right, I mean, okay, I'm going to use the word to make Peter May happy. The homotopy co-limit is a point, okay, right? Fine. Okay, right? It's a bunch of contractible things. That's what the limit is. Okay, it's really interesting. The fixed set here you would see is, already shows, like for, the thing, there's a Z inverting R, a K Z inverting R1 and a K Z inverting S1. They're really interesting, and you're seeing they're having non-trivial rational homotopy types, but are trivial at the prime P and at the prime Q, like Smith theory says. I mean, this was really showing that Smith, wasn't an idiot, despite his own fears. Okay, but now you have this map and you have this finite dimensional guy. So now let's just think about, if I'm trying to find an equivariant map from EZPQ into the space of measures, MK of, I'm just going to call it PQ, right? Well, this thing here is equivariantly homotopy equivalent to EZPQ cross this space X. Okay? And this, of course, has a map to the space X, which is an equivariant map. So I just have to find a map here. Okay, so now you just go ahead and you do it on the fixed set of Z mod P. So you need something, you need the target to be, to be simply connected, because in the fixed set, in this X is 2-dimensional. So if I just have a two-dimensional simply connected complex in the target, I'd have no trouble mapping to it. And then I do that for the ZP, I do it for the ZQ, and then I have to also make sure that the MK of PQ is going to be this X is four-dimensional, so I want that to be four, at least, but it's homotopy equivalent to a three complex, even though it's four-dimensional, right? I mean, so anyway, you can just see that you get 3 times the larger directly. And as long as, just by building it using obstruction, so that goes ahead and builds this. Okay. Yeah, so I think that I probably won't be able to discuss uniform the second topic of the talk, which would have been universal topological complexity. This builds on a notion that Misha and Dan Cohn and I introduced a few years ago about parametrized complexity. We're imagining where you are doing motion planning on X, but you have a space of X's. Okay, so really what's relevant is either the diffeomorphism group of X or the homeomorphism group of X. And the universal space of parameters is an infinite dimensional space. And the point of this talk was going to be for certain manifolds X, despite the fact that you have this infinite dimensional base, the parametrized complexity is sometimes just the complexity of a single fiber, that the parameters don't matter. In other cases, it does. And it's related to similar homotopy fixed set technology. But unfortunately, I don't think that I should go on. I'd rather finish 2 minutes early than a minute late.
Okay, thank you, Shmuel. Are there any questions? Actually, I think the one thing.
Oh, I see there's someone in the chat. Oh,
there's someone in the chat? I don't have a message.
Okay, I see. Yeah.
No, I think that was something else. But I think the one thing that you should mention about the analog topological complexity is the result for RPN.
Mm-hmm.
Namely that when you calculate, you always get 1, or depending on whether it's reduced or unreduced.
Yes. So that was right. I think I had explained that if I hadn't written it down, right? Because you always have, right? I mean, I was calling it 2, but I think that would maybe often a normalization. Right. Because you have to pick one of 2 geodesics in the worst possible case. Yeah. So I think that it's just, right, that the digital one is really, subtle thing, but the analog one is, much more straightforward.
And also, I can't quite get this out of my head that this whole idea seems to me almost like something in quantum mechanics, where we would have a superposition of probabilistic states that somehow lead to a measurement at the end.
Yeah, there was a week or so that I was going to call it quantum complexity, but then I decided that it probably, firstly, it would have seemed like I was trying to be,
avant-garde.
Yeah, right. And I don't think that it really captures, the issues involved. I don't know, evolution of Hamiltonians and being unitary. I mean, it just
exactly.
So Ben is the one who suggested the idea of analog. We had several different ideas in mind about what it was that it was capturing. And,
oops, you froze for a second.
Oh, okay. Yeah, but in the end, we decided to go after that one.
I have a question.
Okay.
Shmuel, thank you very much. Very interesting talk. Very interesting. Question is like this. Do you have general results, or maybe just examples, when this analog complexity is the same as the usual one?
So there's the Eilenberg-Ganea theorem. I mean, I don't have a general theorem. Okay, so the answer is generalities, no. I mean, I just thought about examples. I didn't think about, when could I prove that they're equal? The Eilenberg-Ganea theorem is one where, right, for Lusternik-Schnirelmann rather than for the motion planning analog. So I think that the basic answer to your question is no, Misha, we should really talk about it.
Well, let me mention one thing
Yeah,
from Sasha's work, that a lower bound for what he calls d-cat, for example, is the rational cup length. So whenever the rational cup length gives you the category of the space, then they're all equal.
Right. I mean,
Yes,
so there are things that, I mean, but I don't know what is the general theorem.
Right, I agree.
Okay, thank you.
Any other questions?
So Misha, should we talk next week, by the way? Send me an email.
No private conversations on the recording.
Okay.
Okay, so I'm going to stop the recording right now, but if anyone has any questions, they can continue to ask.